Hi everyone, we're doing Lab 7 Integration Problem 4. So Problem 4 statement says, compute the following integrals for an accuracy of 5 decimal places. Okay, that sounds good. So our integration is going to be -1 to 1 area x dx. Our step size is going to be 1, so h equals 1. Our tolerance is going to be 10 to the -6. So that's going to allow us to get those 5 decimal places. And then our area is going to be 1. Our area is going to be infinite, so and before the while loop, we just want to make sure that we have our area defined and it's any number. And then while error is greater than tolerance, we have our step size h, and we're going to take that and divide by 2, and that's going to become our new step size. So 0.5. And then we're going to have x equals -1 colon h colon 1. So what that is our step size is going in between our -1 and 1. That's what it's doing. Okay, and then we have our area. Our area equals area, comma, traps x, comma, area x. So what is this traps? This traps is, it integrates y with respect to the coordinates or scalar spacing specified by x. So it is a trapezoidal method, and it approximates the integration over an interval by breaking the area down into trapezoids with more easily computable areas. So that y is going to be our area x in this case. And then after that, we understand what our area is going to equal, and so we can compute it. So we're going to do fprint f, and we're going to do that 6 decimal places. It can be 5. The thing says 5, so we can put in 5 right here if we want. It says an accuracy of 5 decimal places, so it's fine. We can round it if we do 6, and then we're going to do area end, so we went to end of the area. And then to find our error, we're going to do error equals absolute values, because we don't want our error to be negative. And then we're going to do our area minus 1. So that's just going to allow us to get that error of what we were missing with the trapezoids. And so as you can see here, this is our area, and there's many solutions right here, because it's going until it finds numbers that like stop and are the same. So as you can see here, it starts at 0.69838, and it goes down to 0.701991, because it's finally going to a whole number right here and not oscillating in between different numbers. So that's that. And then for part 2 on this, we're going to do the integration of 0 to 5 raised to the -x squared dx. So our h is, again, our step size, and that's going to equal 1. And our tolerance is going to be 10 to the -6 to ensure we at least get those 5 decimal places. And our error is going to be 1. Area is going to be infinite again, so we can just, we establish that there is an area, and then it goes into a while loop. So while error is greater than tolerance, our h has to be divided by 2. So our step size is divided by 2, so it's going to be a half. And our x is going to go 0, h 5. And like I said before, this 0 and 5 is coming from the integration from 0 to 5. And so once you get that, we can get our area. And so our area is going to equal area, comma, traps x exp, and then -x dot squared. So that is basically the same thing that we did before with this traps, and then we can finally print it out because we understand what our area equals, and we're going to get 0.886227. And then our error, as again with the same question, we can do error equals absolute because we don't want it to be negative, and then we can do end minus area and -1. So we're just doing it subtracting by 1, and that's going to give us our error. And now we can do differentiation. For lab 7, we can do another problem here. So we're going to go down to problem 2. So in problem 2, it says consider the data set. we have x equals -1 colon 0.25 to 1. So that means we need to get to -1 in a 0.25 steps to 1. Okay, so and then we have our y, and it's going to give us all these y components right here. And this is, the first thing we need to do is do a scatter plot. So that's really easy. So we just do scatter, x, y, o, that we just wanted to, o is just going to be our blue dots over here. We want it to be filled and grid on. So that's what we get right here. Perfect. Okay, now it says, you know that s equals 0. The curve has an angular cusp. Propose a way to compute the derivative that accounts for the cusp. Okay, and so in order to do this, we're going to do the CFD method, which is centered infinite difference. So we're going to find the slope. Okay, so we're going to find the slope to the right and the slope to the left. So the slope to the right is going to be over here. So what we're going to do, we're going to do our y6, which is this point right here, and we're going to subtract it from y5. When you do that, you're also going to divide what that equals, divide by 0.25, which is our step. When you do that, you're going to get the slope right equals -2.5284, which is a negative slope value. And then our slope to the left is going to be y5 minus y4. So that's going to be y5 minus y4. And when you do that, you get the positive slope of 2.5284.